Hi, everyone. Thank you for coming today for our very first talk and the very last talk. This is from Physics Society. I hope everybody has a great time revising. If not, it's going to be a break for you guys today and see what we're going to present to you today. We're happy to have Oleg Brandt to give us a talk on dark matter detection. So
thanks for the invitation.
It's okay. So from 2013, Oleg led a team of researchers at Heidelberg University funded through the Federal Excellence Initiative with a main focus on searches for dark matter at LHC and new unexplored experimental signatures. In 2019, Oleg was appointed at the University of Cambridge, where he extended the scope of his research to include long-lived particle signatures, a vibrant and dynamically developing field due to the unprecedented opportunities in LHC round 3 and its high luminosity upgrade. So without further ado, I would like to present you Dr. Oleg Brandt on his talk about bringing afterlife to life at CERN.
Okay. Many thanks again for the invitation. I enjoy being here. It's nice to talk to physics students and also not physics students. So I think some of you, you may be actually familiar with my face because I tend to lecture electromagnetism, which is a second-year lecture. So I think everyone second year and above should be quite familiar with myself. So yeah, this is kind of showing a slightly different facets of what I'm actually doing in my everyday life. And of course, it looks as glamorous as in these pictures, right? I mean, everything works, nothing is ever broken, everything is fantastic. I hope you noticed the irony in my voice. But yeah, that's essentially the main topic of what we are doing with my team at the Cavendish. So yeah, the title is a little bit enigmatic, bringing afterlife to life at CERN, and I will leave it as an enigma until the end of the talk, and then you are supposed to tell me how this connects to the contents of the talk at the end. Yeah, so the resolution at the end, please. Good. So what is physics all about, right? We're all physicists, so everyone, I'm sure, has asked himself or herself the same question, and of course, I'm also in this position. And I would really like to say it with this guy, and this is Goethe. So that I perceive what holds the world in its innermost folds. Of course, this is just a translation, but basically it is by the way, Goethe was also doing physics a little bit in his free time. Yeah, so he also did a bit on light spectra and things like that. But basically, what we are trying to understand in physics are all structures in the universe from all scales. Yeah, so we want to start from very large scales, the scales of the universe, to the very small scales. And with my research, I'm here, so at this length scales. And of course, the instruments that we use are also very different. So here we start with telescopes, microscopes, and here to probe the really smallest dimensions that are accessible to us, the microcosm, we need to use very high energies, and this is what we need the Large Hadron Collider for. So this is according to the Heisenberg uncertainty principle. We need to use a lot of energy to achieve very high precision and to probe very small dimensions. And then whatever happens here in the collisions, we detect with a gigantic microscope, which is the Atlas detector. So yeah, once again, for me, physics is essentially understanding the universe from the largest dimensions to the smallest dimensions. So universe, Earth, humans, atoms, and then of course, subatomic processes, which are illustrated here with this Feynman diagram. Who knows what this displays? Has anybody been there already before? Yeah, that's the microcosm at CERN. Yeah, so if you ever get to go to CERN, go inside, it's a very nice museum, which is also very interesting to physicists and even people who are doing particle physics. So let's talk a little bit about tools, because if you go back to this slide, you can already see here the tools. So for me as an experimental physicist, everything that we do in physics is, of course, connected to measurements. And when you're measuring something, you need a tool, you need a device to do this. we also have very fundamental principles that guide us, not only in fundamental physics, like elementary particle physics, but in physics in general. And our two basic tools are essentially understanding what the elementary blocks of nature are and what the fundamental interactions between those elementary blocks are. So we essentially follow the reduction principle. And both of those aspects, both the elementary blocks and the fundamental interactions, are governed by symmetries. So if you will, physics is very much a science of symmetries, just trying to understand patterns and trying to organize our observations into symmetries. So let's take as an example chemistry. You know, chemistry is a special case of physics. And chemistry in a few centuries ago, during the Renaissance, that's what it looks like. Yeah, so it was very, let's say, alchemical, very empirical. People were just trying things out without really a guiding principle. But then, after a lot of empirical observations and finding things out and measuring them, at the end of the 19th century, the periodic table emerged, which is really one of the biggest achievements in science of the 19th century. So this explains to us all of the chemistry, in principle, that we can observe. And this is just, let's say, symmetries that we can see. So we have here, for example, the noble gases, et cetera, et cetera. So there are symmetries, but it's not yet understood what is governing these symmetries. So this is the next step. So how do we probe symmetries? Of course, we need to have some kind of empirical probe. And the picture that I like to show here, and if it were an outreach class at school, I would really bring some dough, and I would hide some objects inside this dough, and I would tell to the students, now you tell me what this is, but you're not allowed to open the dough, right? So then you can take a sharp object, for example, this metal pin, and you poke inside, and from the way it scatters off the object inside, you can understand what's inside. And that's essentially what we are doing in particle physics, right? So we take electrons or protons, and we fire them at other electrons, protons, or perhaps a fixed target, and we see how they scatter. And this way, we can draw conclusions about the form factors of the particles that we are bombarding. And this teaches us or tells us something about the symmetries that describe them. And that's precisely what Ernest Rutherford did. Yeah, so he's also closely connected to the Cavendish. Some of you will be quite familiar with his experiments, some not, but I think it's quite important to really understand this. So I'll walk you very quickly through this. So does anybody know what Rutherford received his Nobel Prize for? I mean, obviously, he discovered the structure of the atom. Yeah, so he discovered that there is a nucleus and that there was, let's say, an electron cloud around it. But does somebody know what he received his Nobel Prize for? Not for this. He actually received his Nobel Prize for this thing here. And that's a scintillating screen. Why do I say this? Well, because I'm an experimental physicist. So essentially, the invention of the scintillating screen, the invention of a detector, was the key to study what is how an atom is made, what an atom is made of. So essentially, what he did is he used particles. In this case, these were alpha particles from an alpha source with a collimator. Right? Then he was firing those atoms at a very thin gold foil. And then he was observing the deflection of the alpha particles by looking at the scintillation light from the scintillator. By the way, scintillation comes from scintilla, which in Latin is the spark. So you're literally observing sparks. So yeah, he found that the vast majority of sparks are observed just following a straight line, from which he concluded that atoms are mostly made of nothing. And in the majority of times, the alpha particles are not deflected at all. But sometimes they're deflected, and they are deflected by quite a large angle, and this is interpreted as a very small nucleus which is sitting inside the atom. And when you hit it, you get a large deflection. And if you don't hit it, if you miss it, then you're not deflected at all. And this was essentially, the birthplace, and essentially, the point where we actually understood the periodic table. Why is it made this way? Yeah, so essentially then we understood also, of course, with the advances of quantum mechanics, we understood that all that chemistry is about is just understanding the how of the atom. Yeah, so what's the charge of the nucleus, and how many electrons are there, and how are the orbitals arranged? So what do we have here? We have here a source of particles, a particle beam. We have here a detector. And if you look at modern detectors today, more than 100 years ago at CERN, these are still the two basic ingredients that we are using. We have the LHC, the Large Hadron Collider, and we have our detectors. And that's what I'm going to talk about today. Right. So what are the elementary blocks that we are playing with? I really like this picture because it reminds me of Lego. And the reason why I like this is because this reminds me that our world is made of very basic elements that are, let's say, irreducible. And these are the so-called spin 1/2 particles, the fermions. So we have quarks and leptons. And in this scheme, they are arranged according to their properties. By the way, I have here also the years of discovery of those particles. So everything here in color are fermions, and the Higgs particle is the only exception. It's not a fermion, it's a boson, but yeah, we'll come to speak about this in a second. So then all these 12 particles are arranged according to their properties, in which interactions they participate. So we have here, for example, the quarks, which interact strongly, so they participate in a strong interaction. They also have an electric charge, so they can also interact electromagnetically, and they also have a weak charge. And what this is, I will tell you in a second. So essentially, they can do 3 interactions. And of course, they're massive, so they can also do gravity. So the 4th interaction they can also participate in. Then here we have the charged leptons. They don't have a strong charge, and as a result, they cannot participate in the strong interaction. However, they have an electric charge, and so they feel the electromagnetic force. And here at the bottom are the non-charged leptons, so-called neutrinos, which don't have any charge at all except for the weak charge. So they only participate in weak interactions. They're also arranged in families according to the mass, and this is also quite important for their properties. Now, so much for the elementary blocks. Let's talk about the fundamental interactions. I already mentioned this a little bit. So we have essentially 4 basic interactions in our world, at least the ones that we know of. We have the electromagnetic force. Here, we have the strong force, the weak force, and the gravitation. Going backwards, gravitation, everyone is familiar with. Electromagnetic force, well, this light there, or the laser pointer, is of course the electromagnetic force. And we also like drawing such diagrams. They're so-called Feynman diagrams. And what they do is they give us an idea about the interactions or the process that has happened. So essentially, this funny picture here represents an equation, which I can use then to calculate the probability of this thing happening. Yeah. So quantum mechanics reduces to quantum field theory at a very elementary level. And that's the equation that we can use to describe the interaction of photons. So essentially, you have here the lines for the fermions. So this is one fermion coming in, another fermion coming in, and they exchange a photon, and that's the fundamental interaction. So for example, if a photon from this light interacts with the retina of my eye, that's this. Okay, then the weak force is the same type of diagram with one difference, the mediator particle. So now we have here W or a Z boson. The W boson comes in two flavors, positively charged and negatively charged. So this is the so-called charge current, and there's also the neutral current, which is the Z boson. The fundamental difference between this and this is that the W and the Z bosons are massive. And the consequence of this is that this interaction has an infinite range. I can see the stars 13 billion years away, in principle. This has a very limited range because the mass of those W and Z bosons is very, very high. It's about 80 gigaelectron volts. So that's about 100 times as heavy as a proton. So as a result, this interaction has a very short range. And indeed, it's responsible for fusion and fission processes. So if you're talking about processes in the sun, it's the weak force that is describing this. Then here on the top right, we have the strong force, which is a bit of an odd one because in principle, the force mediators here are massless. These are the so-called gluons, but still it's a very short range interaction. And this has to do with asymptotic freedom and confinement, which I will not talk about today because that's not directly related to dark matter. But let me just say that essentially this strong force is ultimately responsible for the fact that protons and neutrons stick together, are massive, and yeah, essentially explains why we can be here at this point in time. Right. So these are the four fundamental forces. And the elementary blocks we talked about, the fundamental interactions we talked about. And then the next question is, what are actually elementary particles? What is elementary? So there are different opinions about this. And already more than 2 millennia ago, we have Democritus, who came up with the concept of atoms. An atom in Greek is something that's undivisible. It's not, you cannot divide it further. And he saw it. How did he observe it? Does somebody know? So he was looking at the abrasion of steps, which are becoming smaller and smaller. But because the abrasion creates dust that you can't really see, he came up with the notion that there must be little atoms that are undivisible that we carry away when you step on stone. So then he came up with his theory, and well, I will not try to read this up. I will just read up the English version. By convention sweet, by convention bitter, by convention hot, by convention cold, by convention color. But in reality, atoms and void. And that's pretty much this, yeah? We have a lot of void and then some particles, which then have specific properties. They participate in electromagnetic interaction, have a specific charge on the strong direction, have a specific strong charge, et cetera, et cetera. But in reality, the rest is just, void and those elementary building blocks. And that's precisely what this guy was already postulating a few millennia ago. Okay, this is not quite the truth. So let me say it with John Ellis, who is, well, a slightly geeky theorist. But a fantastic person. And basically he's saying fundamental particles are excitations of the quantum field vacuum. Who can imagine the quantum field vacuum? Raise your hand, please. Nobody can imagine a sea? That's what it is. The quantum field theory is just a sea. Of course, there is no excitation. So let's add an excitation to it. That's an excitation. You excite the sea. So that's an elementary particle. It's an excitation of the quantum sea. And this brings us to the concept of elementary particles. What is actually an elementary particle? What characterizes it? Now, this is slightly philosophical, but I think this is also deliberate. An elementary particle, as we can see here, is a discrete state. If it is a discrete state, it is countable. So fundamental particles are countable. And this countable or discrete state is characterized by three things. It's characterized by the mass, or if you will, the energy of the excitation. It's characterized by its angular transformation properties, or as we say in physics, by the spin. And another thing that characterizes it is its charge and couplings. So in other words, if I go back a couple of slides, where in this diagram it fits in. So which charges does it have? In which interactions can it participate, and with which strength? If you give me the mass of the particle, its spin, and its couplings, the rest I can just calculate ab initio, which is really cool. That's precisely what fascinates me personally about particle physics. So essentially what we are dealing with at the current level of human understanding with the most basic elementary blocks of this world, from which in principle, you can calculate everything else, at least everything else in a physically observable universe. Yeah, so these three properties are essentially characterizing our discrete states or our elementary particles. So let's drill down into this a little bit more in detail. So discrete states, it's a point-like state. So to our best understanding today, all fundamental particles are indivisible. Otherwise, we would stop characterizing them as fundamental particles. They are countable. So we can say in this picture, we have how many? 9 electrons. And they are fundamentally indistinguishable. So all of these 9 electrons are exactly the same. In other words, I have my system, 2 electrons at a time A. So I switch on my microscope or whatever, some device to observe the 2 electrons. At time A, I see 2 electrons. Good. Obviously, I cannot observe a system with, let's say, an infinite number of frames per second. So a specific time later, let's say time B, I see this picture. So I see now 1 electron here and 1 electron there. Now, fundamentally indistinguishable. What is the consequence of this? I do not know whether this electron went there and this went there between time A and B, or whether rather this one went there and this one went there. They're fundamentally indistinguishable. And this brings me to the concept of probabilities, because in particle physics, and that's perhaps the downside of it, I don't know. I mean, when I first really understood this, I found it slightly disappointing. We can't really make predictions. We can only make probabilistic statements. We can calculate probabilities, and that's all fine, but we cannot say or state things with certainty. Okay, what else characterizes our electrons besides probabilities? They have a specific mass. Each electron has a mass of 511 kilo electron volts. Sorry for the typo. This is actually MeV, so mega electron volts. So yeah, well, not add, but multiply by 1000. They have a specific spin of 1/2. And they have also a specific electric charge, which is the elementary charge, according to our gauge. And this is minus 1.6 times 10 to the 19 Coulomb. And because they have a charge, I know that they can participate in electromagnetic interaction. And I know that I can write down, well, draw this piece of a Feynman diagram, which is a vertex. So we have 3 particles connected. That's called a vertex. And with this, I can already calculate 1/2 of the Feynman diagram. So I know 1/2 of the equation. Of course, then I can use those vertices to assemble my entire process, following some rules of quantum field theory. And with this ab initio, I can calculate my probabilities. Cool, man. Okay, how are we doing time-wise? Oh, I need to speed up slightly. The standard model in the 1930s. That's how it looked like. Fantastic. Yeah, everything is explained. We have the proton, we have the neutron. Okay, at this point, people didn't really know that the proton is made of up quarks and down quarks. So it's this thing is not quite true. We have the electron, we have the photon. And if I went back a couple of slides, which I don't want to do, not to waste time, you would see that with this particle content, you can explain the entire periodic table. And everyone was very happy. However, there were a couple of problems. And problems are very important in physics because this tells you there is something very interesting to discover. Problem number one, the beta decay. Yeah. So in fact, this was known well before the 30s. So if you look at the electron kinetic energy in beta decays, for example, C14, we all have C14 inside us, which is the radioactive isotope of carbon. If you have a decay, a radioactive decay, you would expect for the electron kinetic energy the value of about 0.16 MeV, sharp. However, what people have found is this continuum. This, of course, didn't really fit with this expectation of a single body decay. And the instruments that led to this, and this is quite important, was the Geiger-Miller counter and a magnet spectrometer. By the way, James Chadwick is also played an important role there. And what we have here is a theoretic proposal, essentially proposing that it's not a two-body decay. So we have the nucleus, the daughter nucleus, and the electron coming out, but also a neutral particle, which, if you read this, was called a neutron at this point, because of course the concept of the neutron was coined only a bit later. So this is what we call today a neutrino. So then if you have a three-body decay, then of course the final state particle doesn't have to have a fixed energy. So this was one proposal. And that's also why Enrico Fermi is in this picture, because he actually calculated this process. So this is a simplified Feynman diagram. So essentially you have a neutron coming in, proton going out, then electron and neutrino. And you can write down this equation, which is essentially the rule how to calculate this. This is the so-called Lagrangian. And if you measure the couplings, you can actually even calculate the probability for this to happen. And that fits the observation. But of course, for this, you really need to make a really theoretic proposal. You need to go away from this very nice, simple picture. And you need to accept that there is an additional particle which you have no idea about, and which is really difficult to detect because it doesn't have an electric charge. It's neutral. That's why it's called a neutrino. The other thing that was discovered, and what makes me particularly proud, is actually this picture here. Have you seen it before? Who has seen it? Who has seen the original? You are studying physics in Cambridge. You should go to the Cavendish Museum and see it. Find this thing. Yeah, this is one of the first bubble chambers. Sorry, cloud chambers. So essentially, Charles Wilson invented a cloud chamber, which was then further developed by Anderson and his friends, also by adding an automatic triggering mechanism. But basically, what they did by sending such, well, not exactly such, but of course, the further developed cloud chambers into the atmosphere on balloons, they found, using also magnetic field, antiparticles. So we have here an electron, which is coming in, being slowed down in this lead plate, and comes out here. How do you know that this is actually not an electron, but a positron? How is this the discovery of antimatter? Yeah? Is that a hint or no? Okay. How is this a discovery of antimatter? And yeah, it's going the other way around, right? So if it came this way, then of course it's inconsistent with the bending radius being smaller here. So obviously the particle came from there because it was slowed down by the lead plate. We know the direction of the magnetic field, and this gives us the charge of the particle. So it has a positive charge and behaves like an electron otherwise in all other properties. Of course, this was not the only observation. They observed more positrons, but basically they've seen electrons that behave exactly like electrons with one difference, that they have a positive charge. So that was the birth hour of antiparticles. So again, here, an important component to this was instrumentation, building a new detector, new capabilities, cloud chamber, and also the possibility to trigger it. Because if you send this stuff into upper atmosphere, you don't want to take pictures continuously. You only want to take pictures when something interesting is happening. So what I'm trying to say is that whenever physics is making advances, it's really a dual play between theoretical developments, but also instrumental developments. And this is also why in our lab, we are developing new detectors. Okay, the standard model today. So this is, as you can see, a few decades after the 1930s, where only a couple of those particles are found. Now the standard model looks much more complete and it's nicely arranged. I mean, this is a picture from a particle physics movie that you may have seen. So basically, we have here in red the 6 quarks. We have here in green the six leptons. We have here the force carriers. We have the Higgs boson, which is quite central because it gives all the particles its mass. We have here the fundamental quantum numbers. Everything looks fantastic, yeah? Nice and elegant, especially with a suggestive red round picture. And if I'm not convincing, then you can listen to Michio Kaku, which is a famous string theorist. And he's also very excited about the standard model because it can explain every piece of experimental data concerning subatomic particles up to about 1 trillion volts in energy. This is about the energy of the LHC and, of course, cosmic ray collisions. This is about the limit of the atom smashers currently online. Consequently, it is no exaggeration to state that the standard model is the most successful theory in the history of science, which is, I think, a true statement. But I already hinted at the fact that this nice harmonic picture is somewhat suggestive. The standard model has many shortcomings. And the same guy says the standard model is supremely ugly. It is like taking Scotch tape and taping a giraffe to a mule to a whale to a tiger and saying this is the ultimate theory of particles. This is why I like doing particle physics. It is nice and neat, the standard model. It's highly predictive. However, it has serious flaws. So let's perhaps start with not the serious flaws, but just with the oddities of the standard model. One of the oddities of the standard model is that the fermion masses are arbitrary. What do I mean by this? I mean by this that a priori, ab initio, we cannot calculate the masses of the fermions. There is no prediction for this. We have the standard model, which is a quantum field theory, locally gauged invariant. Everything is fantastic. We can calculate probabilities for things to happen. But this model has a lot of free parameters. Each fundamental particle, each fermion has a specific mass, which we need to measure experimentally and put into this Lagrangian, into this predictive theory, into the standard model by hand, which is, of course, very unsatisfactory. And not only do we have to measure it and put it in by hand, but also the masses are vastly different. Let's take, for example, the charged leptons. The charged leptons are the electron, which you're all familiar with. So 511 keV is the mass, kilo electron volts. or half a mega electron volt, then 100 times that is the mass of the muon, and about 2,000 times that is the mass of the tau lepton. So this is represented here in this picture. The height of the columns represents the mass, so the electron is very small. Here's the muon, here's the tau. So yeah, we have no real explanation why the tau lepton is so much more massive than the electron. No idea. Why is the Higgs boson so light? This is, let's say, a variation in the theme, but a very grotesque one, because the Higgs boson, as you know, gives all of these particles their masses, which means it can couple to all of these particles. Then, if I follow this argument, the Higgs propagator, when I write down the equation for the Higgs boson to propagate in space, it receives virtual corrections from all particles that it can interact with. And I need to put this into the equation and consider this. Now, the issue is, because the Higgs is a scalar and can in principle interact with all particles of the standard model, these corrections can in principle be quite arbitrary. And if you put this into the equations, you realize that the Higgs mass could have easily been as high as 10 to the 19 giga-electron volts. And yet, it is only 125 giga-electron volts, similar in mass to the W and Z bosons, and let's say to the mass scale of this diagram. No explanation for this. Either there is some extreme fine-tuning at the level of, let's say, 10 to the minus 19, or there's some fundamental explanation which we have no idea about, at least as of today. Just to give you an idea about this, this riddle with the electrons and the taus and the top quark and the charged particles, they're all here, right? And this is a logarithmic scale, yeah? So we have no idea how to explain this. What is even more grotesque is that the neutrinos are somewhere here. Count the orders of magnitude: 1, 2, 3, 4, 5, 6. 6 orders of magnitude lighter, yeah? So everything else is there, neutrinos are here. I mean, not only we don't understand the differences here, but also we don't understand the gap. There are several models on the market which may explain this, maybe not. In the next couple of decades, there will be an update, I hope. So yeah, stay tuned. Some more oddities of the standard model. So let's talk about this, let's say, Lego style plot. So it shows the mass flavor structure of the fermionic sector. So the lightest particles are here on the left. This is the first family. The second family are the ones which are a bit heavier. And the third family are the most massive ones. So first of all, if you look at this picture, you find something odd. There are 3 families. Okay, pick a number, 3, fine, 3 families. But why are there 3 families for quarks, and the same number of families, also 3 families for leptons? Why do they have to have the same number of families? We've searched for the 4th family. In fact, we search still for the 4th family of quarks or leptons at the LHC. No sign of it. Odd, eh? Why are leptons generally lighter than quarks? No idea. Then, if you look within the families, and if you look just within the quark sector, each of those pairs can, in principle, interact with the W boson, so with a charged current, so weak interaction charged current. They prefer to interact within the family, which, okay, I'm happy to accept, but they also interact across families. So for example, the up quark and the strange quark can also interact with the W boson, or the up quark and the B quark can interact with the W boson. And those probabilities we parameterize in terms of this matrix. It's the so-called CKM, Kobayashi-Mascaba matrix. And the sizes of the rectangles give us the probabilities, right? Why does it look like this? Why not different? Why does it like these diagonal couplings? Why are these couplings so tiny? Now let's look at the leptons, yeah? So we have the same here. Why does it look like this in the lepton sector? And why does it look different from the quarks? No idea. Now let's come to speak about serious problems. Yeah, I mean, this is all kind of, yeah, things we don't really understand. We don't really have an explanation for it. It's not a serious problem. It's a shortcoming. Serious problems. One serious problem is why are we here? Obviously, we are here, we exist, we are alive. However, if you just take the standard model and you put it in and you calculate everything with a super predictive theory, what this theory tells you is that after the Big Bang, you produce matter and antimatter in very close to equal proportions. Now, you know what happens if you bring matter and antimatter together? They annihilate, create two photons, gone. So if the standard model was the truth, then we would have produced pretty much very same amounts of matter and antimatter in Big Bang. They would have annihilated, and we would just have photons this time. Perhaps slightly, a slight remnant of matter. However, we have quite a large, not large, still very small, but orders of magnitude larger difference in the numbers of particles as opposed to antiparticles that survived. So we have tried to look in the universe as far as we can look for signs of perhaps antimatter parts of the universe. And then, of course, the signature that you're looking for is that antimatter, the boundaries between, let's say, matter parts and antimatter parts, there would be, of course, annihilation between the two. So you would expect to see photons, those annihilation photons from the boundaries. Yet we don't see this. So as far as we can tell, all of the universe is mostly made of matter. And we have no idea how so much matter could have survived after the Big Bang. In principle, according to the standard model, almost all of it should have just annihilated with antimatter. By the way, the Feynman diagram for this is mostly that. So you have particle, antiparticle, two photons. Serious problem. No idea. Another serious problem. I like to show this picture with an iceberg because that's about how much of the iceberg is above the surface of the water. So this is 10 to 15%, depending on the salinity of the water. So yeah, what we see in this picture, what we see is just 15%. The other 85%, no idea about. And because we are really, in the dark with our hypothesis how it could look like, or because we're just stupid, we have no better name for it but dark matter. Yeah, so we just call it dark matter. And what I've been doing the last decade is to search for this. So how do we know dark matter is there? There is lots of evidence, but I will just walk you quickly through my favorite evidence. So this is Vera Rubin, and essentially what she did was to provide the first version of this graph. And what this shows is a galaxy here. And what you're plotting is the velocity of objects orbiting the galactic center as a function of distance. So you can look at this galaxy with a telescope. You can look at the visible matter. You can also look at the hydrogen, which is mostly out here, right? And then you can plot it, and that's what you measure. However, if you just take the hydrogen and the visible matter, what you expect is this. So what you measure is here, what you expect is here. And what is missing is, well, some additional mass. We call it dark matter. That would be responsible for essentially explaining why the rotation velocity is so much higher as you go out from the galactic center. Now, this you can still kind of tweak some Newtonian dynamics and say, okay, notch scales, maybe it doesn't behave the way it we expect it to. But then what these type of explanations really miss to explain is the dynamical processes, like, for example, here in the bullet cluster. Who has seen this picture before? I assume most of you will have seen it, the bullet cluster. So who has seen it? Hand up, please. Okay, a couple of people. Okay, so this is quite famous. So what it shows are two galaxies that have just collided with each other. Okay, just collided means few millions of years ago. And basically, what you can see are two measurements of the mass of those galaxies. So first of all, what is shown in blue is, let's say, fake color representation of the actual mass in these galaxies. And you can get it from the gravitational lensing of the galaxies which are in the background. So from these observations, you conclude that most of the mass of those two galaxies that went through, so essentially what has happened is they went inside and passed through each other. This is what happened. So they just undisturbed went through each other. Very little interaction, dark matter. And what you see here in red is the excitation of the atomic hydrogen clouds. And of course, being regular matter or standard model matter, as I call it, they interact with each other. And yeah, you see a lot of X-ray emission from this region. So there are two components, dark matter, which just went through each other, didn't interact much, and then the rest. Strange. No explanation. So, and this brings me to the second part of my talk, which is how do we search for dark matter? And being a physicist, of course, I'm trying to be fair. I'm not only talking about my stuff and my corner, but I also try to explain a little bit what the other people are doing. So there are different ways to search for dark matter. And the way I like to talk about it is using Feynman diagrams. You may have noticed I love Feynman diagrams. And the funny thing about Feynman diagrams is that you can draw them up, and they can have different meanings depending on where how you let your time run. So this is the same Feynman diagram, as you can see. This circle in the middle represents, well, some interaction between the particles, which I don't want to specify at this stage. And then I can let the time run from left to right, from bottom to top, or from right to left. And depending on how the time runs, I have different detection mechanisms. So let's talk about this one here, the indirect detection first. So essentially, I have two dark matter particles, which will be called chi for the rest of the talk, colliding. Time runs this way, interacting with each other. So they come together, they interact, and then there's a pair of fermions coming out. So this is indirect detection. So essentially what my signature, what I'm looking for, are those two fermions or the result of their interaction. Okay, how does it work? So essentially, I have here my fundamental processes, and then I go into space, like, for example, with the AMS spectrometer on the International Space Station, and I look for those fermions or for the signs of the annihilation of those fermions. For example, I can look for photons, or I can look for electrons or for positrons. In particular, antimatter is quite interesting because what comes out from this Feynman diagram is in equal proportions matter and antimatter. Okay, matter is not so interesting because we have a lot of matter in the universe. As I already mentioned, we have a matter-dominated universe. But when I see a lot of antimatter coming out from these processes, then this can be quite interesting. And that's precisely the reason why this is the money plot from AMS. This is the positron spectrum. So not the electron spectrum, but the positron spectrum. And that's what they measure as a function of energy in giga-electron volts. So this is going up to 1 tera-electron volt. And what you see here is this dependence, which you can parameterize with a diffuse term and a source term. So far, this is completely empirical. This is just what we measure, and this is the parameterization. However, what is quite interesting here is that this source term has a cutoff. Yeah, so it rises and then falls off again. And this is what makes people so excited, because if your dark matter particles were producing something with energies of about 1 TeV, then 1 tera-electron volt, then you would expect fermions with about 1 tera-electron volt, or, well, not electrons, but electrons and positrons, and that's what you measure here. Yeah, so it's kind of localized, and this is what makes people so excited. It's not just a continuum. Yeah, of course, there are also other explanations, potential explanations. So it could be that this is coming from, not necessarily from dark matter annihilation, but from quasars or something like this. People are looking into this. This is a very active area of research. And of course, what is particularly exciting is to get more data from AMS and also get independent confirmations from other experiments. What you can also do, and that's a little bit the issue here, with the positrons, it's impossible to trace them back to the source. Why? Why can we not? Why is it so difficult to trace the positrons back to the source where they came from? Any idea? They're indistinguishable, but what will also happen with an electron or a positron, which is charged as it propagates through space? Yeah, it can annihilate, that's right. But also, what do we have in outer space? Is it completely free of any fields? No. We'll have magnetic fields. They'll be, of course, very, very weak, but then the propagation distances are enormous. So as a result, all the positrons will follow, let's say, a non-straight track. And as a result, it's really impossible to really point them to a specific source. However, what also will happen in such Feynman diagrams are processes where photons are being emitted, either as final state radiation or as part of fragmentation of the final state. And I deliberately don't go into details into what exactly these terms mean. But then, of course, you can point them back to their origin. And this is precisely what the Fermi the Fermi satellite has done. So essentially, it was searching for photons from the galactic center, from dwarf spheroidal galaxies. And this allows you to probe for dark matter annihilation, because, of course, dark matter is expected to annihilate primarily where there is a large concentration of mass. So at the galactic center or in dwarf spheroidal galaxies. So there is such a thing which is called GCE, which is the galactic center excess. And yeah, we are now waiting for the next generation of satellites to really, and also ground-based observations to really understand this a little bit better. Okay, so much for indirect detection. Now, direct detection. Direct detection is you let the time run upwards. And essentially, you have the photons, the dark matter particles scatter off standard model particles. And this is really a microscopic process, which is happening at the level of a nucleus. So you have here a dark matter particle coming in, scattering of the nucleus. The nucleus has a recoil. And yeah, then, of course, that's what you measure. But what can also happen is that you simply have photons which may interact with the nucleus, and this then gives rise to your backgrounds. So this is the type of detectors that you have for this. So they're typically supercooled detectors, because any excitations may be confused with a signal. So they're supercooled materials, the target material is supercooled, and also very radio pure. So typically these experiments are very deep underground, so 1 kilometer or deeper. And also they're made of very radio pure materials. So there's a lot of, let's say, R&D, research and design, going into those detectors to identify materials which are not radioactive, which have very tiny residual amounts of radioactivity. And then these materials are purified, brought underground, et cetera, and the detectors are constructed. So the limits that you get from this is how they look like. So this is the mass, the hypothetical dark matter particle, and this is the cross-section for this scattering process. And what you're trying to do is you're trying to set limits in this scattering cross-section. So the smaller cross-sections you can exclude, the better. Yeah, because smaller cross-section means a smaller rate of interaction with dark matter. And that's also quite exciting, because in a couple of years, well, not a couple of years, but let's say within a decade, we'll hit some fundamental limitations with this technology. And yeah, the community is very excited, because there's really an expectation that either we will see something until that time, or it will be a hint that what we are looking for is perhaps not quite how nature has decided it, let's say. Okay. I see that with my detailed explanations, I'm going a bit over time, so I'll try to wrap up very quickly, and perhaps I will not go really into detail for the rest of the talk, but I still want to give a rough overview about collider production of dark matter, because that's what we are personally doing with our team, and that's very close to my heart. So the fundamental process for this is you're colliding fermions, and you use the same Feynman diagram, so you expect them to produce dark matter particles from these interactions. And that's the fundamental assumption. And of course, then you need some apparatus to measure those dark matter particles. And what we use for this is, for example, the ATLAS experiment. That's the one I'm working on. There's, of course, the CMS experiment, et cetera, and all of them are situated at a collider, at the Large Hadron Collider in this case, because that's the thing that provides us highly energetic fermions and antifermions. So in this case, there are, for example, quarks and antiquarks, which are collided. So this is how it looks like. I look for my dark matter particles. However, the problem with dark matter particles is that they're dark matter particles, so they don't interact with the detector. So how do you detect them? You can infer their presence by looking at standard model particles. So essentially, if I were to extend this Feynman diagram, and there's a third particle produced as part of this process, a standard model particle, that guy I can measure. And then I can infer the presence of the dark matter particles. How do I do this? Any idea? It's a very fundamental principle in physics. So if I measure in my detector just a standard model particle and nothing else, highly energetic standard model particle, maybe 100 GeV or so, and nothing else. Yes, exactly. So conservation of momentum. So I look at the transverse plane in my detector, which is represented here. Yeah, so I have here my standard model particle, which is recoiling against the system of the two dark matter particles, which remain undetected. That's the guy I detect. And the momenta of those dark matter particles are summed to give us the missing transverse momentum. So the missing transverse momentum is the vectorial sum of the momentum of the dark matter particles, which is minus the standard model particle momentum. So far, so good. So which standard model particle would I want to use for this at a Hadron Collider? And I have this Feynman diagram. So you can imagine that this is a quark and this is a quark, which annihilate. Okay, quark, anti-quark to be precise. So what is this standard model particle what is going to be most likely? A particle which interacts electromagnetically, weakly, or strongly. It will be likely, well, quark was the suggestion, it will be most likely a particle which interacts hadronically, yeah, because these are strongly interacting particles. The strong coupling is the largest one. So essentially, we are looking at diagrams where there is, for example, a gluon radiated from the initial state. Yeah, a gluon will hadronize, will form a jet of hadrons, which we can measure in our detector. And yeah, this will be then what we measure on this side. And on this side, of course, there will be nothing. So there will be missing transverse momentum. So how can I extend this Feynman diagram? We already said through a gluon. So jet or several jets, photons. You can also radiate a photon off here. Then, and this is present in all models, yeah, because I can always have initial state radiation. Then in many models, I have W or Z bosons, which are coming either from initial state radiation or from, let's say, this hard interaction, which is indicated by this circle. Or in some models, I can have also the Higgs boson, which, however, cannot come from initial state radiation because the rate for this is very, very low. So these are typically models where the Higgs is produced directly as part of the hard interaction. And just to conclude for today, I just want to explain how typically such dark matter searches work at the LHC. So this is an event display, so to say, or a sketch of what you've seen before on this slide. So essentially it's that. So we have here the two protons coming in, colliding. These are the dark matter particles. This is the missing transverse momentum, and this is the jet that it is recoiling from. And that is a Feynman diagram for a potential process that could have happened. Yeah, so you produce your dark matter particles at the end through a new mediator. And of course, this you can calculate, you can predict, and that's what we use to guide our searches and to interpret them. So the signature that you're looking for is missing transverse momentum, recoiling against the jet. And so what you'll be looking at is the rate of events as a function of missing transverse momentum. So how much missing transverse momentum is carried away by the dark matter particles. So then your standard model prediction is essentially, yeah, the phase space, which is an exponential-like function. And if you see an excess, so you measure more than you predict, then you're happy and you say, yay, I found dark matter. However, there's a problem. You know, in physics, there's always a great idea, and then there's always a problem, because otherwise physics wouldn't be physics, it would be just engineering. In engineering, there are no problems, there are only solutions. In physics, there are only problems. So first of all, how do these events look like? So this is an event display from Atlas. So you have here the calorimeter cells, and the height of the calorimeter cells represents how much energy is deposited there. So you can see that there is a very energetic jet in the one hemisphere of the detector, recoiling against a lot of missing transverse momentum on the other side. And it's a real event. It's a real candidate event, which was recorded by Atlas. You can even see the event number and the timestamp. It's from 2017. But it unfortunately doesn't mean that we've discovered new dark matter. And the reason for this is because there is this problem. And the problem is illustrated here. The problem is that we have a standard model process that looks exactly like this. So we can produce a Z boson. The Z boson couples to neutrinos through the weak interaction. We know that. We can even calculate the probability for this because that's a Feynman diagram. You know the Feynman rules. We can write down the Lagrangian for this process. We can calculate the probability. And unfortunately, the probability for this to happen is fairly high. I mean, still not too large for LHC standards, but that's your irreducible background because the final state is exactly identical to what you're searching for. That's the issue. So what do we do? The only thing that we can do is to measure this and this at the same time. And that's what we call a control region. So we define not only the signal region where we are searching for our signal, but we also define a control region where we are measuring our background process. How can we measure our background process? Well, very easily, because the Z boson doesn't really care how it decays, right? It can be also charged leptons. So if it were charged leptons, we could easily measure this very precisely. And we could use this knowledge to really constrain this background process. So this reduces our uncertainties, and we can make very precise predictions about the contribution of this process to our selection. And that's precisely what's done here. So we have here the missing transverse momentum as the number of events as a function of missing transverse momentum. So this is precisely the plot that I was talking about before in the signal region. Yeah. And this is the same plot in the control region. However, here, this is not the missing transverse momentum. This is the momentum of the Z boson as reconstructed from the decay of the Z boson into a pair of muons, which we can measure. So we can really use that to constrain this process. However, there's a problem number two. Problem number two is, if you look at the y-axis here and here, you realize that we have about 1.5 orders of magnitude fewer counts on the right-hand side. So we have a statistical problem. And the statistical problem is coming simply from the small branching ratio of the Z boson, which likes to couple to neutrinos, 20% branching ratio, and doesn't like to couple to charge, to charge leptons. So what do? We have another control region, which is shaded out here, which is the one lepton control region. And this, of course, will see contributions from W bosons plus jets. And of course, W bosons are not the same as the Z bosons, but they're very similar. They're charged currents, neutral currents, but they're both weak particles. And so you can use the W plus jets process, and you can calculate, in theory, the differences between W and Z boson predictions. So calculating differences is always easier than making absolute rate predictions, which is why we have control regions. You want to measure things in situ, but then calculating differences is possible. And this was done at next to leading order in the strong coupling, with next to leading logarithmic corrections, and a next to leading order in electroweak couplings. And what this all means, we can teach you if you choose to do particle physics in your fourth year. Right. So then if you do this, you can set very stringent limits, which you can see here. So they're typically expressed as a function of the mass, hypothetical mass of the dark matter particle, and the hypothetical mass of this mediator here. And then you can make such nice Brazilian flag plots with green and yellow colors. And you can essentially say this region here below this curve is where dark matter is not within the context of this model. Or, for example, if you have alternative models, again, you can interpret your findings within the context of these models. Right. So this is just giving you a little bit of a flavor of how we are searching for dark matter at the LHC. I think I should come to a close because, yeah, with the detailed explanations which I tried to give, we ran out of time. However, I promised you a riddle at the very beginning, so we should do this. So let me just skip forward. So the bottom line of all these Feynman diagrams that I was showing you is that it is exciting. There are some things we don't quite understand, but we didn't see dark matter yet. So until the next generation of more precise experiments goes online, of course, we don't sit with our arms crossed at the LHC, but we look into alternatives. And one of those alternatives are so-called long-lived particles. So long-lived particles are hypothetical new physics particles, which are produced and which are long-lived. Long-lived, of course, not on human scales, but let's say on collider scales. So they have lifetimes of, say, order of 1 nanosecond, up to 1 second. Now you could say, and by the way, they're actually quite challenging to search for because that's not what the LHC detectors were built for. They were built to search for prompt production of particles. So why long-lived particles? They're constrained by astrophysical observables and beam dump experiments. However, if you look at the standard model, you see that there are many long-lived particles. So in fact, what's shown here is the mass of the standard model particles on the x-axis, and here the lifetime, c tau, in meters. So it's essentially tau, the lifetime, in seconds, times the speed of light. Yeah, so you can see here a lot of particles which are very short-lived, which decay essentially immediately. Then you have some longer-lived particles and 3 particles which are essentially, within, as far as we know, with an infinite lifetime. Electrons, neutrinos, the proton. But then there's a lot of particles up here which are quite long-lived. So they have lifetimes of 1 nanosecond and longer. So then, if you see this in the standard model, this range of lifetimes, then the question becomes, why the hell the dark sector, which hosts the dark matter particle, why should it be trivial? Why shouldn't there be more states in the dark sector? So for example, maybe there is a dark matter particle, which is long-lived and light, but there may be also additional states, which I call LLP here, so long-lived particles, which have different masses and different lifetimes. If you make this assumption, that your dark sector is non-trivial and contains not just one particle, the dark matter particle, but more particles, then this opens new avenues how to search for this. Because if you produce these guys, they will be unstable. They're long-lived, right? So these guys will want to decay into the dark matter particle and then some other stuff. And the other stuff will be standard model particles, which you can measure in your detectors. So when you produce one of those, your signature becomes nothing, because they're dark sector particles and they're long-lived, and as long as they live in the dark sector, you don't see them, but eventually, because the lifetime is finite, they decay. So you see the decay products, the dark matter particle which they decay into as well. You don't see, of course, but then you see the standard model ones. And that's your signature. So this is just an overview of all the possible signatures you could use with the current detectors like Atlas to search for long-lived particles. Yeah, so essentially this is your signature. Yeah, you collide two protons, you produce a pair of long-lived particles which travel outside without generating a signal and then decay, and you measure the decay products. That's the idea. So I'm skipping forward. Basically, these are the limits on such scenarios. And I will not really explain the plot because we ran out of time. But basically, the message is that everything that is above these curves is excluded. And this looks fantastic because, of course, this plot was made by Atlas. I'm also part of Atlas, so this is why I'm allowed some irony, right? And this plot shows you how fantastic a job we did and how much we've excluded, and this is all great. However, the issue is that the cosmological bounds which restrict the lifetime, c tau, they come in here. And that's 6 additional orders of magnitude. And of course, because Atlas made this plot, we chose to terminate the axis here, right? And it doesn't say anything about this question mark. And the reason why this is so difficult to probe is because our detectors have a finite size. So if c tau is large, then of course, if your lifetime is large, then of course the decay will happen further and further away. And at some point, it will just happen outside of the detector. So you will not be able to detect it. So that's a fundamental limitation of the LHC experiments, because as I said, they were built with prompt signatures in mind. They were not really built to search for long-lived particles. And that's precisely why we proposed an extension of the Atlas detector, which is Anubis, as you can see from the picture, from the Chacal head. And okay, we can't really push all the way down to cosmological bounds, but yeah, I think this is still quite some improvement. So I think when we publish our plots, we will terminate them here. Right, this brings me to the end of my talk. So I've skipped again a couple of slides, and we are back to the riddle. So what does Anubis have to do with the topic of today? Well, obviously, we proposed this experiment and it's an extension, et cetera, et cetera. This is why Anubis, but then why did we choose Anubis? You know, physicists are great at shoehorning acronyms into some funny name, right? For example, this is also why the Atlas detector is called the Atlas detector. It's not because it's a toroid or something, yeah? So why did we come up with Anubis? And what does that have to do with the title of the talk, The Afterlife? Any suggestions? Has to do with the last slides of, let's say, the last 10 slides of the talk. That's right. You're producing long-lived particles which exist, let's say, in the afterlife. Yeah. You don't see them because they're dark sector particles, and then they decay into standard model particles, which you can see. So they come back to, let's say, to being alive, right? And if you look, if you read up on Egyptian mythology, Anubis, which is obviously this guy here with the shackle head, you know what his job is? If you're a good Egyptian, you know, and you had a good life, and you were properly mummified, then, I mean, this is a mummy, right? I mean, only then, right? Then he helps you to cross the river of death. Yeah, so he takes you by the hand, like you can see here. He has also the key to the gates of the afterlife. And then what is not shown here is a gigantic scale, which I didn't fully depict because I didn't want to be gross. So on one side of the scales is the heart of this guy. And if you look up how mummies were made, you will realize that the heart was taken out and placed separately. Why? Because, you know, as they believed, after you die, your heart would be weighted. And if you were a good person, your heart would be light and everything would be fine, and you would be allowed to emerge to life in the afterlife. And if not, then there's, I don't remember the name of this god, but basically it's something with a crocodile head, right? So this thing is getting to eat first your heart and then yourself. Yeah. But then, of course, if your heart is light enough, Anubis, who is sitting here at the scales, checking and everything, then this guy is helping you to come back to the afterlife, and that's precisely what our detector is doing, right? So if your particles, if your long-lived particle decays into standard model particles, then the Anubis detector can help you to detect it and to bring your long-lived particles into the standard model world, where we can actually see the decay products, register them, and hopefully discover dark matter. That's it. Thank you. And sorry for going over time. Yeah, you tell me whether we do questions. Sorry. If it's late. If no question, that's also fine. It's late. I mean, yes, please.
Since we have, say, like 85% of dark matter in the universe, then
Yeah.
do we have any observable effect of the dark matter on the orbit of Earth that we have already detected?
In the orbit of Earth, no, not necessarily. So you start seeing this on, let's say, galactic scales.
Oh, so like
Yeah. So if you go back to the picture with Vera Rubin, the distances here are typically, megaparsecs. Where is it? Yeah. So this is the distance in light years. Yeah, that's where you start seeing it. So about, let's say 5,000 light years. That said, you can actually still search for dark matter by using the indirect detection approach.
Yeah.
So you can search for it by looking either at annihilation in the center of galaxies. Yeah. So this is what these guys are doing, but you could also search for dark matter annihilation inside the sun, because the sun is our local center of gravity in our solar system. So if there were dark matter in our solar system, you would expect it to be accumulated around the sun. So there are searches which are looking for this. Of course, the different search strategies have their strengths and weaknesses depending on the model assumptions, but this is actually an active area of research.
So does the current, say, like progressing telescopes, does it help with, say, the gravity lensing? So like detect the dark matter with gravity lensing?
I would say yes and no. Gravitational lensing by now is so well established as a technique, and we have such precise measurements from Hubble that there is no doubt that dark matter is around, et cetera, et cetera, et cetera. I think James Webb is more interesting in the sense that we can, of course, add additional precision, increase the precision. And also what James Webb is quite interesting for is that you observe, of course, more galaxies, and some of them are quite odd. So then you can actually try to study the outliers. And for example, there are a couple of candidate galaxies which seem to have less dark matter than the rest, which then, of course, if you see several of those, you would be able to try to see some pattern, like how do they emerge? Is there something that perhaps led to a deficiency of dark matter in these galaxies? Is this an anomaly? Is this just a mismeasurement? Things like that. Yeah, but I think the big picture with James Webb doesn't really change.
Thank you again for this very interesting talk.
Yeah, just on something you said. Is the distribution of dark matter sort of confined more to certain areas than others, or is it isotropic?
Yeah, I mean, essentially, this is what this plot tells you, right? So this tells you about the radial distribution of dark matter inside the galaxy. And there are models for this. So there's even a model for the radial distribution of dark matter in our own galaxy, in the Milky Way. So if it were not so late, I would skip to the slide to actually show this to you. But I'm happy to make the slides available. You can have a look at it yourself later.
If there's no more questions, then thank you very much for this informative and interesting talk. And Thank you, everybody, for coming tonight. Let's give another round of applause to Dr. Brandt.
Okay, thank you. I really enjoyed it. Thanks for